Students, today I am going to continue my lecture on the quantum mechanical operators, and let's start from the inverse of an operator, which is denoted by, say, A is an operator and a to the power minus 1 is the representation of the inverse, which is defined as by this relation where A and A inverse or A inverse A, that is commutated to each other, will give you the unit operator. Unit operator means that operator which operates on psi will give the psi back with no eigenvalue, that is with unit eigenvalue, and importantly positive plus 1 eigenvalue. You can say it will produce, that is the unit operator. So if this equation is hold, then A inverse will be called the inverse of the operator A. And in case of matrix algebra, you know this thing, that is the inverse of an operator. How we will get it? If the determinant of any matrix is non-zero, then you will assign the inverse of that matrix, but if it is not, then you can't assign the inverse of that matrix. So here, yes, it is written over here that by this formula you can do, because in quantum mechanics the operators can be represented by the matrix. So this thing is written over here. If you want to represent the inverse of the operator in matrix mechanism, then you should find the adjoint of the A matrix, then divide by that adjoint of that matrix by the determinant of the given matrix A. It will give you the A inverse, that is the inverse matrix of the operator A. And obviously you can check this relation also, like matrix, the inverse is that is AB whole inverse will be B inverse into A inverse. So they will change their position, that is the inverse of an product. And now the very important from the quantum mechanical perspective, the unit operator. The unit operator defines as an operator, a linear operator, U operator will be unitary if its Hermitian conjugate and its own product is equal to the unit operator, that is U dagger U is equal to I or U dagger is equal to I. See here, in the case of inverse, that is A inverse or A inverse A is equal to I. So obviously the unitary operator, if this relation holds, then you can say that the dagger, that is the Hermitian conjugate of the unitary operator, is obviously equal to the inverse of that operator. So U inverse is equal to U dagger, you can say, for the unitary operators. And now see the some properties, that is if U and V are two unitary operators, then their product is also an unitary. You can prove by this way, that is UV dagger whole dagger into UV, that is UV whole dagger gives you in the opposite manner, that is V dagger into U dagger, and UV is there. So U dagger U will be I, so I into V will be again V. So V dagger into V is again I, because U and V are both unitary operators. So what we will get, that is their product is also unitary, because UV whole dagger into UV is I. So UV, that is the product of the two unitary operators, is also an unitary operator. These are the advantages of unitary operator, which can be exploited in the further quantum mechanical developments. Similarly, you can show this thing. Now let us take some examples on or important properties on unitary operator. The first one, show that the eigenvalue of the unitary operator is equal to 1, that is the modulus of eigenvalue, that is it can be minus 1 or plus 1. So proceed this way. Here psi n, another thing, yes, that doesn't have that the eigenfunctions of unitary operator that doesn't have any degenerate eigenvalues, that is the eigenvalues are different, so the eigenfunctions must be orthogonal. That should be proved. Let us start by taking two eigenfunctions psi m and psi n corresponding to unitary operator u operator, and it has two non-degenerate eigenvalues, that is for psi m it is lambda m and for psi n it is lambda n, and you can write, it is not written over here, you can write simply that is u psi m is equal to lambda m psi m, and u operating on psi n will give you lambda n psi n. So these are there, and start from here, that is psi m star psi n d cube x, that is the integration over all the space minus infinity to plus infinity. You can avoid this because it is all over the space. Yes, it is correct in Cartesian coordinate system, but not other dimensions, coordinate systems. So here d cube x can be think of, that is dx into dy into dz. Okay, then this integration is correct, and remember that is there are three integrals, but one is shown here. So psi m star psi n d cube x. Now here you can say that is identity operator is there, I operator. So in place of I operator you can write u dagger u by the definition of unitary unitary operator, and take u star with this psi m in a bracket and u over psi n in another bracket. And now what is that? What is this? Psi m star means psi m dagger. So you can write this, that is u dagger, u operator operating on psi m whole dagger. It will give you in the previous step, you can see that is psi m dagger. Psi m dagger means psi m star, because here psi m is a scalar, psi m star, and multiplied by u dagger. Okay, so this line is correct, and now put the eigenvalue formula here. U m, you can put lambda m psi m, u psi m you can put in this, in case of u psi m you can put lambda m psi m, but as there is a whole dagger, so lambda m star will come out and psi m star will be in the integral. Similarly here lambda n psi n, lambda n come out of the integral, and this is now this is wrongly written, this is not 0, this cannot be written here. Okay, this is the step. Now take this integral at the left hand side, and this will, or this one to the right hand side, this will give you lambda m star lambda n minus 1 into whole integration is equal to 0. Now if n is equal to n, then this one will give you lambda n square or lambda m square. So for this will be 1, because this will be this is the from the probability interpretation, the psi n star into psi n whole space integration will give you 1. So lambda n square minus 1 will be 0. So lambda n is equal to mod of lambda n or lambda m is equal to plus minus 1 1. So this will be plus or minus 1, the value of lambda m. And if n is not equal to m and they are non-degenerate, that is lambda m and consider this, if n is not equal to m, then the only possibility of this equation to be 0 is that this is not always 0, because if lambda n is not equal to m, then this will be there, but you cannot guarantee all the time that this one is 0. So for all cases this one is not equal to 0 for the all time, so the integration should be 0 all the time, that is integration over psi m star psi n d cube x is equal to 0. This means that the two wave functions corresponding to eigenvalues, non-degenerate eigenvalues lambda n and lambda m, they are orthogonal to each other. Okay. Now another important operator is the parity operator. Parity means the operation of the space inversion, that is we can change the variables from one space to another, that is r to minus r by reflection, you can see. So as a result, as we change the coordinate systems such that r becomes minus r, so the wave function, which is a function of r vector, goes into function of r minus r. So now if psi of minus r is equal to psi r, then the function psi r will be called even, or if psi of minus r is equal to minus of psi r, then the function will be called the odd or antisymmetric, then the function will be called in the odd parity, and the previous case the function will be called in the even parity state. Now in algebra you can write that psi of minus r is equal to p operator over psi, that is p is the parity operator which can transform the psi from r to minus r. It is very evident from this equation. This is not the eigenvalue equation because the wave function is not reproduced. So this is the basic transformation relation between psi r and psi r minus r. Now some problems on parity we can deal with, that is show the parity operator is Hermitian. Now let us write the parity operation which I have written here without the Kate notation, that is p operator operating on psi r will give you psi of minus r, and here you can see I have written it by the Kate relation, that is pi operator. Pi is the parity operator here, and operating on x will give you minus x. Now recall the completeness formula and use this. How? Bra x operator, parity operator and Kate x prime will give you, in place of pi x prime you can write minus x prime using this relation. So x minus of x prime will give you delta of x minus of minus x prime, that is x plus delta. This is the Dirac delta function. So this is using the continuous basis. You know from my previous class I have discussed all about this, the completeness condition for the basis Kates in the continuous basis. So this is delta x plus x prime. Now if you reverse the bras and Kates and take the complex conjugate, then it will give you x prime in bra and minus x in the Kate and whole star. That means, what is this? This is nothing but x of, by this formula you can write also, that is x delta of x prime plus x again. So these are two same things. So this expectation is equal to, actually this is yes, this expectation is this equal to this expectation, and by the definition of Hermitian operator you can see, you can go to your previous lectures, you can see that is, this is the definition of Hermitian operator, that is pi can be Hermitian if it satisfies such a relation, x pi x prime is equal to x prime pi x whole star. So you can write that pi is Hermitian, that is it is equal to its own Hermitian conjugate, that is pi dagger is equal to pi. So parity operator is Hermitian operator. Now it is also unitary operator. You can prove it very simple way, and I am leaving this up to you to understand this. And now it is very interesting that you can prove that parity operator, the main motto I am explaining here, that is just prove that parity operator is its own inverse. Okay, so P is equal to P inverse, and again you have proved that P is equal to P dagger, that is its Hermitian conjugate. So P dagger is equal to P inverse, so it is simply can be said that they are, that is parity operator is unitary. Okay, and also the eigenvalue of the parity operator, you can prove that it is plus minus 1. Okay, so parity can be either even or odd, and this is the actual proof of the next problem, that is prove that the eigenfunctions of the parity operators have a definite parity, that is it should be even or should be odd all the time. Sometimes some functions do not have parities. Okay, just like e to the power minus x, you can't say about its parity, but you can say that cos x is even parity function and sin x is an odd parity function. So if parity operator operates on a function, then the function should have the definite parity, that is even or odd. That is our proof. So let us take step by step, where P square operator is identity operator because it is proved in the previous formula, that you can see P square means P operating on P on psi, and now psi minus this will give you psi of minus r. Next P operating on psi of r minus r will again flip its sign of r vector, that is psi r will be given. So P square operating on psi r will give you psi r. Now P square, so what is happening there? P square operating on psi r will give you psi r, that means P square is operating like just the identity operator. Okay, so P square is written as identity operator, so unit operator you can say, I operator. So its eigenvalues are plus 1 and minus 1, it is proved in the previous problem. So let us express the eigenfunction corresponding to the eigenvalue plus 1 is psi plus. On the other, so you can write P operating on psi plus will give you 1 into psi plus r, while for the other, that is again from the definition of P, you can write P operating on psi plus r will give you psi plus minus r. So it will follow that eigenvalue is 1 because eigenvalue is plus 1, you have taken that. Because of this, the eigenvalue relation becomes this. This is not eigenvalue equation, this is the definition of parity operator. So if you compare both of them, you can write psi plus r is equal to psi plus of minus r. So psi plus is for the eigenvalue, psi plus is the eigenfunction for the eigenvalue plus 1, and this is definitely the even parity function, that is even function. Similarly, you can show that for the eigenvalue minus 1, you can get the eigenfunction which is odd. So parity operator have definite parity, that is either even or odd. It doesn't make any function in between, that is neither or odd nor even. You can get this. Okay, we are looking at the measurement perspective of the observables. Here the topic is complete set of commutating observables. I have discussed earlier that if the operators are commutating operators, that is computable operators, they should have simultaneous eigenfunctions. And here in this topic I will describe why is that so, and why we cannot assign a simultaneous eigenfunction to the non-commuting operators, and what is the measurement difficulties in such cases. And for this, let us discuss the problem for measuring more than one observable on a system in a given state. Okay. So let us take such operators A and B, and suppose we want to measure these operators, that is we want to measure the dynamical variables A and B on a system which is in the state of psi. Since the operators do not commute, the result obtained by the measuring A first and then B will differ from the measuring B first and then A. Okay. And let me explain the reason behind it. Let us suppose first A, we are going to measure A on the state psi, and operating A on psi, it will give you the nth eigenstate, that is I mean to say here, that is I have discussed earlier for the in the topic of measurement in quantum mechanics, that if you operate an operator on a system, on a state, then the measurement will come out at a definite state. As you going to measure the system, you will disturb the system, so the system will be assigned at a particular state which will come out of the experimental as an experimental result. So let us take this state as nth eigenstate of A, that is you will get the eigenvalue an if you operator A operate on psi. So so an is your eigenvalue when you operated A on psi, and with the eigenstate psi n. Psi n is among the psi state, that is psi is expanded into basis set expansion of phi n, and you fix the system, or you get the system when you operate A operator on psi, you get the result on nth eigenstate, that is you get the eigenfunction phi n with the eigenvalue a n. Now since A and B do not commute, phi n is not an eigenstate of B operator. We have done this problem earlier. So if you now operate B on phi n, because now the state of the system is fixed at phi n, because you have already operated A on psi. Actually you are trying to operate here B operator, A operator on psi. So A operator psi on psi fix the system at phi n with eigenvalue a n. So you have now the eigenfunction on which the operator B will operate is phi n. Okay, but phi n is not the eigenstate of B. So that is why B will if you operate B, then the measurement cannot be predicted in advance. That is, what will be the state after operating B on phi n, because phi n is not the eigenfunction, so there will be mixed up. Now the eigenvalues Bm you will get with probability Cnm, and Cnm is the coefficient of expansion of phi n into the series with respect to chi m. Say chi m is the eigenfunction of B, so phi n will be expanded into the basis set expansion of phi n, and when you operate B on phi n, then say phi m eigenstate will come out of the experiment with the eigenvalue Bm. Okay, so the final eigenstate you get operating both B and A, first A then B on psi, will be chi m. Okay, now we reverse the sequence of measurement, that is operate B on psi. If you operate B on psi, then suppose the eigenvalue Bj come out of the experiment with the eigenstate chi j, where chi's are the eigenfunction of B. Now same problem, chi j is not an eigenstate of A, then if you operate A on chi j, then the eigenfunction will be in any one of the phi m, where phi m is the eigenfunctions of A. Okay, you can see first that for A operator I have written that the eigenfunctions of A as phi and eigenfunctions of B as chi. So if you operate, I am again repeating my explanation here for the reverse sequence of measurement, that B operates on psi, it will give you chi j, which is the eigenfunction of B with eigenvalue bj, and the system is now fixed at chi j, and another operator A operator will be acting on chi j, but chi j is not the eigenfunction of A. So chi j can be expanded into the eigenfunction or basis set expansion of the eigenfunction of A, that is phi m, and the results will be any one of them. So the results will be the eigenvalues will be all possible eigenvalues of A, that is A1, A2 dot 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 anything anything possible. So all eigenvalues are possible, so a single eigenvalue not will come out of the experiment. So the eigenvalue or eigenfunction will be the most unpredictable in this case when you operate A on chi j. So you can see for the first case the last outcome, that is B operating on phi n, will not guarantee that the eigenvalue will be Bn. It will be B1, B2, B3, any one of them with probability Cnm square. And in case of reverse measurement, the final outcome is, we cannot say the final eigenvalue, whatever it may be, the A1, A2, A3 dot 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 Am, anything value with the corresponding probability Cjn. So the results are different in case of this measurement, the final result, and for this case the final results are very much different to each other in general, we can see. So that is why those operators, if two operators do not commute, they do not have the simultaneous eigenfunction, and the measurements cannot be done with certainty, that is we cannot sure shot tell that An and Bn eigenvalue will come out of the measurement. So at the final stage the eigenvalues will be unpredictable, and here, if A and B will commute, what we will see now, let us suppose A and B commute, okay, then they have simultaneous eigenfunction, that is phi j for will be the eigenfunction of the jth state for all A and B. Now if the system is at the state psi and you operate A on psi, then the eigenfunction will be phi n with eigenvalue An, and the rest of the operator is B operator. Now phi n is fixed with eigenvalue An, and if you operate B on phi n, it will give you eigenvalue Bn with again producing the eigenfunction phi n, because phi n is also the eigenfunction of B. So B operating on phi n will give you the eigenvalue Bn reproducing the same eigenfunction phi n. So if you measure B operator, A operator on psi, if you operate this, that is you first measure A operator, then you measure the B operator, the final eigenvalue will be of the problem will be An Bn with the eigenfunction phi n. And in reverse case you can go reverse case, the result will be the same. So the measurement is very much certain when the operators are commutating operators. Okay, So that is why the corollary is written, that is compatible observables, that is commutating observables can be measured simultaneously with any desired accuracy. I can tell you that phi n will be the result with eigenvalue a n and b n, while non-compatible observables cannot be measured simultaneously. That is, when you going to measure a first then b, the result will be such unpredictable, but the unpredictability is not repeated when you measure in the reverse order. So to get I can summarize this topic that we should get complete set of commutating observables for the simultaneous measurement of different observables at a time. So we should have the knowledge which operators are commutating, so we can measure them with great accuracy. Now we are heading towards the degeneracy discussion. As I have already pronounced this term degeneracy several times, but here we are going to look what is the degeneracy mean. Suppose A is an operator and phi A is an eigenfunction of it with eigenvalue A. If the eigenvalue is degenerate, okay, degenerate means A eigenvalue will come out from different functions also for the operator A. Okay, sometimes eigenvalues are called the eigenvalue spectrum, and those eigenvalues can be discrete or continuous, as I have discussed earlier, that the discrete representation, continuous representation, all things are there. So eigenvalues come out of this, but I am now focusing here whatever the eigenvalue is. It is discrete, it is continuous or semi-discrete, semi-continuous, whatever it is, but it is degenerate, that is, it is coming out of many more eigenfunctions for the operator A. Suppose phi A and chi A are two eigenfunctions on which A operator operates, this A operator operates to give you same eigenvalue, that is small a. So the linear combination of those two eigenfunctions will also be the new eigenfunction. We can prove it. Say C1 phi A plus C2 phi chi A. C1, C2 are constants. Let us operate A operator on this function. So it will give you, see, it is distributive law, as A is a linear operator. So A phi A will give you small a phi A, and A operating on chi A will give you small a chi A. So small a is taking out of the bracket, so C1 phi A plus C2 chi A. So this eigenfunction, see, this eigenfunction is reproduced again, those are same. When A operates on this this function, it will give you same eigenvalue A, reproducing the same eigenfunction. So in this manner we can, as C1 and C2 can be any constant, so this is not describing a single eigenfunction, this is describing infinite number of eigenfunctions. So actually the degeneracy will be the infinite set of eigenfunctions. Okay, so we can take infinite type of linear combination of eigenfunctions, but in this case, as two functions are degenerate to each other, so this is called twofold degeneracy. Similarly, you can get r-fold degeneracy when such functions give you the same eigenvalue when operating on operated by a same operator A. That is, and you can set up so many linear combinations of those functions to get the new eigenfunction. Okay. So here it is written R-fold degeneracy. Now some problems are there, physical problems. I will discuss it when I go to the section of Schrodinger equation. I will discuss it. Now simply for the sake of mathematical interest, you can consider, suppose there is a differential equation of an wave function phi, and here all the terms are constant except x and phi. And if you solve this is SHM equation, you will get the two kind of results, e to the power I alpha x and e to the minus I alpha x. But when you operate this operator d2 dx2 on this function, you will get alpha square, and when you operate on this, you will again get alpha square. So the alpha square, or here the minus alpha square, so minus alpha square is the eigenvalue which is doubly degenerate, because it is coming out of two different functions, and you can get linear combination, you can add them up, so you will get cos, or you will subtract then you will get cos. So sine, so sine, cosine, they are also the solution of this equation with doubly degenerate. See, so they are doubly degenerate in all the way. Now the last topic of our this discussion is a generalized Heisenberg uncertainty relation. What we have studied here, the operators, different operators, expectation values, and the commutation relation in quantum mechanics, all boils down to this generalized Heisenberg uncertainty principle proof. Actually, this is not the proof of Heisenberg uncertainty. It cannot be proved in any way, because we have our predetermined some results, and we will use them to get the Heisenberg uncertainty relations. As it is called generalized because the treatment is very much generalized, for any operators it is true, but keep in your mind that Heisenberg uncertainty relation, it is satisfied here, not it is proved. This is not proof of Heisenberg uncertainty relation. So we can satisfy generalized Heisenberg uncertainty relation. So let us follow this technique. Let two Hermitian operators A and B corresponding to observables A and B, and the state vector psi is there, whatever it is, it may be a continuous basis state or the discrete basis state. There is no as such category on this state vector. Now let A expectation value of A, what is that? Psi A psi, and what is B? That is psi B psi. This is the measurement of A and B, you know this, and psi is normalized to unity. So this is the expectation value formula for A and B. Then the uncertainties in their measurement can be written by statistical rule, that is delta A is equal to root underscore, that is, it is called root mean square deviation from statistical mechanics. You can follow this formula, that is A square expectation value minus expectation value of A, that whole squared. This is the deviation, and root mean square of that deviation is called the uncertainty by definition of A. Similarly for B is there. So we should calculate this quantity to get delta A, that is uncertainty in delta A and uncertainty in B, because Heisenberg uncertainty relation deals with the uncertainties in dynamical variables, that is uncertainties in momentum, in position, in energy, in time, etc., etc. So uncertainties will be measured here. So these quantities are very much important, and let us now introduce two new operators, delta A and delta B, which is the deviation actually. that is A, or variance, that is A minus expectation value of A. This is not operator, this is actually a scalar function. Yes, it is operator, you can say it is a multiplying operator, and A is the your basic dynamical variable operator. So A minus expectation value of A and is delta A operator. Similarly, delta B operator is B operator minus expectation value of B. So these are the new operators we have defined for our sake of simplicity of the calculation. So if you operate them on psi, it will give you another scalar function phi. No, here scalar it is written in terms of ket. So delta A operator operates on psi ket, it will give you phi ket. Similarly, delta B operator operates on same psi ket, it will give you in general different eigenket chi. Since the operators A and B are Hermitian, so there is an inequality that is called Schwarz inequality, which I am not going into detail. Just remember this formula. This is called Schwarz inequality, that is, this is actually length of the vector phi, this is actually length of the vector chi, and their product will be greater than equal to the inner product, square of the inner product of the phi and chi vectors. So this is very much looks like your complex number identity, but here it is called Schwarz inequality, and we use this because what is phi phi? You can here you can see, here you can see, I am coming to this line later. Now phi phi, so you can you have phi ket, so you can find the bra of phi. So sandwich them, that is inner product of phi phi, that is the length of the phi, and it will be surely psi delta A square, as they are Hermitian. So delta A dagger into delta A means delta A into delta A, that is delta A square, and psi is in the ket. It is obtained from this relation, and similarly chi chi is obtained from this relation. From your bracket algebra you can get this, and keeping in mind that delta A and delta B operators are Hermitian, that is why no Hermitian conjugate is there, they are equal, so whole square is there. Similarly, phi chi will be this. Now you can put this directly on, or now let us see what is this. Psi delta S operator A square psi in ket. This means this is the expectation value of delta A operator square. So this is written here. Okay. Now chi chi is the expectation value of delta B square operator. So in place of chi chi it is written that is expectation value of delta B square. And in the right hand side it is the simply it is just put it down here, the mod is at the outside of this inner product term, and this is also an expectation value of the product of delta A and delta B. Now the product delta, this is the master stroke I should say, delta A into delta B, delta A operator into delta B operator can be written as half of delta A comma delta B commutator bracket plus half of delta A comma delta B of anti-commutator bracket, because the second term, that is delta B delta A, here you can expand this delta A into delta B minus delta B into delta A, and if you expand this delta A delta B plus delta B delta A, so second term of each bracket will cancel each other and half is there, so it will add up to give you delta A delta B. So it is a master stroke, and you can see here that is delta A and delta B in commutator will give you, simply because delta A, what is that? This is the formula of delta A. If you commute delta A and delta B, these terms will be cancelled to each other because they are scalar. So these terms, no terms related to this will come out or exist in the commutator bracket. You can verify it, this is up to you. just expand this, just in place of delta A put this formula, and in place of delta B put this put this formula. You will get the result, that is this and a commutator will be half of the commutator between A and B, nothing else, and this one is written as it is. Now this is A and B are two Hermitian operators, so their commutator will give you their commutator will be anti-Hermitian, and the anti-commutator bracket of the Hermitian operators are Hermitian. It has been proved earlier in my problems. I have proved it. Okay, no, sorry. So you can find from my previous lecture that I proved it, that is the commutator bracket of Hermitian operators is anti-Hermitian, and anti-commutator bracket of Hermitian operators are Hermitian. So it is opposite nature, and we know that expectation value of Hermitian operators are real while the anti-Hermitian operator is imaginary. So when you get have written, because I want to find this value, that is the expectation value of delta A delta B. So the delta A delta B I have got this. So expectation of delta A delta B means half of expectation of AB plus half of expectation of this. Now expectation of this one is your imaginary, and expectation of this one is purely real. So we you can purely make this value imaginary, or you can purely make this value real by multiplying I in the respective places. See here, it is giving you the expectation value of this anti-commutator will give you the real number because it is Hermitian. So if I multiply it I, so it will give you the imaginary value, and this will also give you an imaginary value. And now using the complex number technique, you can find that the mod square of delta A delta B expectation value will be the mod square of this plus mod square of this, because this is z is equal to x plus iy. So mod z square will be x square plus y square simply. So this is written here, this is the squared and taking the mod, and this value squared and this value squared except I. So this is the general formula. So it is the sum of two terms. So we can write that delta A delta B expectation mod square will be greater than equal to the first term. You can see, you can write any time. So we have got this result, that is this one is greater than equal to 1 by 4 of this expectation value of A and B commutator brackets. Now yes, look at this expression where in the right hand side is that term and the left hand side you keep left hand side unaffected, but you change the right hand side using this law. So you can see the left hand side is delta A square expectation into delta B square expectation, which is greater than equal to this one, that means greater than equal to 1/4 of commutator expectation value of the commutator of AB, and it is mod square. Now it can be simplified also. Delta A expectation delta A square expectation using delta A formula. Delta is what? A square minus A, that is it can be expanded into this. Just put delta A operator, yes, this one, delta A operator into this formula, okay, into this expectation bracket, and distribute the expectation bracket, you will get this result. Here see, they are equal, so A square minus A square. So at the beginning we have defined it as the uncertainty, that is delta A square. Similarly delta B operator square expectation is nothing but the uncertainty of delta b of b, that is squared value of that. So in the left hand side, delta a whole square into delta b square is greater than equal to 1/4 of a comma b whole square, and if you take a root of the thorough equation, so you will get that delta a into delta b is greater than equal to half of a comma b, that is its expectation value. Now let us take an example of the position and momentum. You know the result, that is rj comma pk, that expectation will give you I h cut into delta of jk. If j and k are not equal to each other, then it will be 0, and if they are equal, suppose for x and px, it will give you I h cut. Okay, so generally it is put here. So delta r j and delta pk, what will be that? Half of expectation value of commutator bracket rj comma pk, and here rj comma pk we can put this I h cut, which is constant, so there is no point in writing the expectation. So I h cut delta jk will be the result, but I here it is mod, so I will be gone, and h cut by 2 in h cut by 2 into delta jk will be the result. If you put delta j and k equal to each other, so this will be 1, so delta x into delta px will be greater than equal to h cut by 2, which is the famous Heisenberg uncertainty relation. And there is another Heisenberg uncertainty relation between energy and time, and but this is formulated in different way. Okay, so how is it is defined? Let a is any operator, any dynamical variable, and E is the energy. So delta A into delta E is greater than equal to half of mod value of expectation of the commutator bracket of A and H. Here H is the operator form of E. Now H is the Hamiltonian operator, you know. Now from the Heisenberg equation of motion, we will prove it later. For the time being, just assume this equation: ddt of A, expectation value of A, is equal to 1 by IH cut into expectation of the commutator between A and H. Now put this A comma H expectation using this equation here, so this will give you this result. And if you divide dA dt into the left hand side, so right hand side will be h cut by 2, because in there is a mod, so I will be cancelled, so h cut by 2 in the right hand side. Now look at this thing, this is delta A by d dt of A, so the dimension of A will cancel each other, will cancel, and the dimension of this one is nothing but time, so we can write this as time interval delta tau. So this is delta tau and delta E, which is greater than equal to h cut by 2. This is the famous uncertainty relation between time and energy. Okay, here my discussion on the operators and the commutators and the measurement and the commutating set of variables, and also the generalized treatment of Heisenberg uncertainty principle concludes, and I should thank you for listening.